Hello everyone, welcome to the Tim Booker channel. Wishing you all an enjoyable listening experience. Today, the book I'll be interpreting for you is called The Last 3 Minutes. This book delves into the topic of how the universe will meet its demise. The notion of the universe's demise might sound like a scene straight out of science fiction novels. In our conventional understanding, the universe is perceived as something eternal. However, as scientists delve deeper into their studies of the universe, they increasingly discover that the universe as a whole is subject to the constraints of physical laws. These laws dictate a life cycle for the universe. It is born, evolves, and will eventually face its demise. If you want to comprehend the birth of the universe, we've previously interpreted a popular science book titled The First 3 Minutes. It vividly describes the initial moments of the universe's birth. You'll notice some resemblance between that book and the one we're discussing today, one focusing on the first 3 minutes, the other on the last 3 minutes. The Last 3 Minutes, authored by the world-renowned physicist Paul Davies, reflects his profound enthusiasm for studying the universe. His inspiration for delving into this field stemmed from the book, The First 3 Minutes, when he was young. One could say that Paul Davies aimed to create a companion piece to the initial 3 minutes by crafting The Last 3 Minutes. These two books encompass the entire lifespan of the universe from beginning to end. I'll break down the content of this book into 3 parts for you. 1. Why scientists firmly believe the universe will inevitably head towards its demise. 2. The various conjectures scientists have regarding the demise of the universe. 3. How scientists aim to ascertain which of these conjectures is the most plausible. What will be the ultimate demise of the universe? Let's start by addressing the first question: why do scientists believe the universe is destined for extinction? Today's scientists have an array of tools at their disposal to study the universe, be it new theories or new technologies. With the aid of these tools, scientists have indeed concluded that the universe is heading towards its endpoint. However, back in the 19th century, nearly 200 years ago, scientists, devoid of today's advanced concepts and tools, inferred that the universe must have an endpoint through just 2 thought experiments. Let's explore these fascinating thought experiments. The first, called Olbers' paradox, was proposed by a German astronomer named Olbers. He posed a question that puzzled the astronomical community for years: why is the nighttime sky black? At first glance, you might not see it as a problem. The night sky lacks the sun and only consists of stars and the moon, which aren't as bright as the sun, hence darkness. But upon deeper thought, you'll realize it's not that simple. Both the sun and most stars at night are essentially stars. Let's assume all stars have the same brightness. Other stars seem dimmer because they are much farther away. If a star is twice the distance from Earth compared to the sun, its brightness is just 1/4. If it's 3 times the distance, the brightness drops to 1/9. The decrease in brightness is proportional to the square of the distance. Now, if we assume the universe is infinite and stars are uniformly distributed, we can envision an imaginary spherical shell around Earth. Doubling the radius of this shell quadruples the number of stars it encompasses. The increase in the number of stars compensates for the decreasing brightness due to distance. If the universe were infinite, countless stars, no matter how far, would shine on Earth like countless suns. So why is the nighttime sky dark? The only plausible explanation is that our initial assumption was wrong. The universe isn't infinite, and stars aren't infinite in number. Our universe, vast as it is, has boundaries and mass. The second experiment was proposed by the German physicist Hermann von Helmholtz, a master figure in the history of physics. Based on the previous experiment, he formulated another one using the second law of thermodynamics. This law states that in a closed system, heat always flows from a higher temperature to a lower temperature spontaneously, and this process is irreversible. You might argue about air conditioning on hot days, but that's because our rooms aren't closed systems and have external interventions. Imagine bringing the outdoor unit of an air conditioner into a sealed room with all windows and doors shut. Now, if you run the air conditioner, while one side cools, the other side heats up. The room's temperature won't decrease. The same principle applies to the universe. Heat flow is unidirectional. A prime example is the sun, which constantly radiates heat into space, never to be retrieved. Eventually, the sun's energy will deplete, and its temperature will equalize with its surroundings. Some scientists even tied the second law of thermodynamics to the concept of time, stating that the flow of heat mirrors the direction of time. So, why does the second law of thermodynamics allow us to infer the future of the universe? Because, based on the previous thought experiment, we've established that the universe is a closed system with finite space and a finite number of stars. Despite its vastness and complex planetary movements, the second law of thermodynamics will perpetually influence the universe. Heat will forever flow from higher to lower temperatures. Hermann von Helmholtz concluded that inevitably, in every corner of the universe, temperatures will become uniform. Consequently, the universe will cease to have any meaningful physical activities. It will be like an exceptionally flat body of water, unable to flow or exhibit any ripples. Scientists coined a term to describe this universe resembling a stagnant body of water, heat death. In Helmholtz's view, the lack of heat flow in the universe will lead to its eventual stagnation. This signifies the ultimate demise of the universe. However, more than 100 years have passed since Hermann von Helmholtz's era, and today's scientists have experienced revolutionary changes in their understanding of the universe. So, let's move on to the second question: what conjectures do modern scientists have about the demise of the universe? The first conjecture continues from the earlier heat-death hypothesis, and scientists have found stronger support for it, the Big Bang theory. Scientists have discovered that today's universe originated from a massive explosion. The universe began expanding from an extremely dense point and has been continuously growing ever since. Modern scientists have deeply studied the Big Bang, as depicted in the book, The First 3 Minutes. In this book, scientists precisely describe the changes occurring in the universe within the first 3 minutes after the explosion. Many of the universal laws governing today's universe stem from the effects of the Big Bang. One such effect is the ongoing expansion of the universe. Scientists have observed that distances between galaxies are gradually increasing, indicating that if this expansion continues, the future universe will not only have uniform temperatures everywhere but will also have lower temperatures as it grows larger. It could even approach absolute zero, at -273.15 degrees Celsius. Near this temperature, particle kinetic energy decreases, rendering matter less active. Thus, the universe's expansion will accelerate its descent into silence. This is the first conjecture of the demise according to today's scientists. However, with deeper exploration of the universe, scientists have introduced a second theory about how the universe might meet its end. Some propose that the universe won't continue expanding infinitely, as those who believe in eternal expansion overlook a crucial factor: gravity. Observing dying stars nearing the end of their life cycles, scientists have noticed a phenomenon called gravitational slingshot effect. When a dying star is influenced by gravity, it slowly drifts toward the center of a galaxy. During this drift, it interacts with other stars, mutually attracting and forming unique orbits, often described as a romantic embrace due to gravitational forces. If a third star or planets come into play during this interaction, the movement of these three celestial bodies becomes incredibly complex and unpredictable. Even the orbits of these three stars cannot be precisely calculated. This concept mirrors the setup of the famous sci-fi novel, The Three-Body Problem. As a result of the gravitational slingshot effect, dying stars are highly likely to contribute their massive energy to one star, ejecting it like a projectile from the galaxy, an enormous release of energy. This star might even get captured by a black hole. Stars that remain within the galaxy would ultimately merge into massive black holes. Under the influence of this effect, the final destination of a star is highly probable to become a part of a black hole. As more and more black holes form and grow in the universe, the gravitational slingshot effect would intensify, leading to more stars sliding towards these black holes, triggering a cascading chain reaction. The ultimate consequence would be the universe transitioning from expansion to contraction, almost like reversing the Big Bang. The universe would eventually return to an infinitely dense point. Some scientists even propose a more radical idea, that our universe might fall into an infinite loop of expansion followed by contraction. Is it possible that our universe's starting point, the initial Big Bang, was derived from the collapse of a prior universe? This amalgamation of expansion and contraction is known as the cyclical universe model. Like multiple lifetimes, each new cycle of the universe arises from the death of the prior one. This conjecture is challenging to validate because if we assume the cyclical universe model, everything from the previous universe would be utterly destroyed when compressed into a point. Today, in our universe, we cannot find any evidence to support this. However, if we assume the cyclical universe model and continue this line of thought, an even more remarkable conclusion emerges: the duration of each subsequent cycle might surpass the previous one. Scientists have discovered that the Big Bang leaves behind significant heat radiation, termed the universe's cosmic background radiation. Over billions of years, the radiation from stars accumulates. Eventually, after several billion years, the accumulated radiation in the universe's space would almost match the cosmic background radiation. This suggests that when the universe contracts again, the excess radiation energy comes from the matter within the universe. This conversion of matter into radiation leads the universe from contraction towards demise. It appears like the reverse process of universal expansion, but with differences, as the universe might be similar in size to before but with less matter and higher radiation. The gravitational effects of this excess radiation differ significantly from those of matter, causing the universe to collapse at a faster pace. If this pace rebounds in a certain manner, the next universe will expand even faster. In other words, with each subsequent Big Bang, the energy should be greater than the previous one. Consequently, with every new cycle, the universe expands to larger scales, and the cycles become longer. So, after discussing various conjectures about the universe's end, expansion, contraction, and a combination of both, it leads to a new question: how do scientists determine which conjecture is the most plausible for the ultimate demise of the universe? Let's imagine a far-off future, say, 100 trillion years ahead. What would the universe be like then? By that time, most of the stars in the universe will have burned out, leaving it dark. However, it won't be devoid of matter. Countless black holes, neutron stars, and black dwarfs will persist. But the density of celestial bodies in this era will be incredibly low because the universe will have expanded by 10 quadrillion times its present size. During this expansion, gravity will engage in a tug-of-war. While the expanding universe attempts to pull everything farther apart, the gravitational forces between celestial bodies strive to bring them together. It's akin to a tug-of-war, and the outcome depends on the density of matter in the universe. The lower the matter density, the stronger the force of expansion. Conversely, higher density increases the force of aggregation. Scientists can estimate the universe's volume and deduce its size, and then, the pivotal factor determining its fate, its mass. Determining the universe's mass seems like a daunting task. We can't weigh each star individually, nor do we have a giant scale to weigh the entire universe. However, scientists have a method. They believe gravitational theory can provide a calculated estimate, not incredibly precise, but it can help ascertain a lower limit for the mass. How do they do this? By measuring the sun's gravitational impact on planets to determine its mass. Today's scientists estimate the Milky Way hosts around 100 billion stars, assuming each star has the same mass as the sun. From this, we derive a lower limit for the Milky Way's mass. Further calculations reveal approximately 100 billion galaxies in the universe, leading to an estimate of the universe's total mass being equivalent to 10 to the power of 21 solar masses. This lower limit defines the universe's mass. In other words, the universe shouldn't weigh less than this value. According to calculations based on this density, scientists find it relatively low. If the universe indeed comprises only this much mass, it will continue expanding forever, ultimately heading towards the heat death scenario. However, many scientists believe that the observable matter in the universe represents only a fraction of the actual matter. Unseen entities like dark stars, planets, and black holes contribute to the universe's mass. Does dark matter exist in the universe? Does it possess mass? Questions regarding numerous abundant yet extremely tiny particles, such as neutrinos, remain unanswered. Today's scientists lack the means to provide accurate answers to these questions. Only when these uncertainties are resolved can we precisely calculate the universe's true mass. There's another group of scientists proposing a radically different model of the universe. They argue that envisioning the universe as a uniform, giant entity during discussions about its future overlooks its highly uneven density distribution. Could it be that our universe can be segmented into smaller units? Each unit would exhibit distinct changes due to its different densities, much like bubbles. Some bubbles expand rapidly, some remain unchanged, while others contract. This model, known as the cosmic bubble model, was proposed by Russian physicist Andrei Linde. He suggests that the universe might not have originated from a single point but from many bubbles. The most intensely expanding bubbles rapidly occupied the largest space in the universe. According to Linde's model, the interior of our current cosmic bubble exhibits a nearly uniform distribution of matter and energy. However, outside our bubble, other bubbles exist, rendering the universe seemingly chaotic on a larger scale. In Linde's model, the expansion never halts. Even if some cosmic bubbles contract, new ones continue forming. This presents an alternate form of an eternal universe, more intricate than the cyclic universe model we discussed earlier. In this universe, life, hope, and the universe itself are eternal. Each bubble might experience life cycles, but the cosmic game of thrones continues endlessly, with vigorous competition among the bubbles. Robust youngsters overthrow old kings, perpetuating an eternal cycle. Presently, aided by current scientific technology, whether it's the heat-death theory, contraction, cyclic universe, or cosmic bubble models, they all remain conjectures. Accurately predicting the universe's future at this moment seems nearly impossible. We can only hope that future scientists will gain a clearer understanding of the universe, leading to a more precise comprehension of its future. Here, I've decoded the essence of the last 3 minutes for you. Lastly, I want to share a fascinating concept I encountered in the book. We've discussed various ways the universe might end. The author raises a question: is there anything humans can do to slow down the universe's demise? At first glance, it seems we can't do anything. Humans, despite our power, can't defy the laws of physics. On the cosmic scale, we're no different from ants. However, the book proposes an alternative perspective. Perhaps we can't delay the universe's end, but we can find a way to transform ourselves. Elevating the speed at which humans process information and our metabolism might hold the key. Because, for humans, time is a relative concept. If our minds and bodies are fast enough, a few minutes for us could yield the effects of several years. In principle, if we could enhance human information processing and metabolism, the remaining time could infinitely expand within the human brain. With this technology, even if the universe has only 3 minutes left until its demise, we could experience millennia in that time. Humanity could essentially attain eternal life. If this technology were to become a reality, the last 3 minutes might not seem as terrifying or desolate for humanity. That's the essence of this book. Congratulations on completing another book. Thank you for your support and attention. Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with your friends. Let's combine wisdom and practice to achieve our financial goals and create a better future. Thank you all, goodbye.